Yeah, so just first off, I want to thank you all for filling in the mid-semester evaluation form. This feedback is super useful to the course and the department. So anyone who took the time to fill that out, thank you very much. We have flicked through it, and most of it is pretty positive. We have identified places we can improve. One common issue that was coming up was that office hours are usually very, very busy. And while generally this is true, it's only true right before the assignment is due. Office hours a week before the assignment is due are like actually empty. So if you want to guarantee yourself space in office hours, going to those earlier office hours is definitely a good place to start. Additionally, if you're in in-person sections, the in-person office hours that are hosted on Saturdays have been like actually empty. So you know, if you're in an in-person section, I would really recommend using that time to seek help.
Okay, thanks, Daniel. Let's get started. Today we are going to talk about the mixed models and the EM algorithms. So it's going to be a continuation of last lecture on the classroom problem. So let's look at this graph again, right? So as I said, we've been, discussing how to, for example, group all these points into clusters, and we run over a algorithm known as the k-means. And today we're going to provide you a little bit more theoretical insight into what is happening behind this very smart heuristic called k-means, and what may be a more general version of that. Okay. So before I do that, I don't know how much we've covered about some of the basics in statistical terminology and formulations. Here, I want to give you a very, very quick overview of some key concepts, a review of some key concepts that we are going to use today to derive some of the formulas. Okay. We know how to toss a coin. It is a way to instantiate the value of a random variable, which is binary. And you can actually describe the probability distribution, of the outcome using a Bernoulli distribution, which is taking 0 and 1 with probability p. And the way to write down the probability of a tossing outcome, a coin tossing outcome, is this: p to the power of x times 1 minus p to the power of 1 minus x. As you can see, this x is binary. It can be 0 or 1. Therefore, when it is 0 or 1, only one of these two terms will be honored. The other will be basically reduced to 1 because the power is 0. Right? And then a little bit more general than that, we have a distribution for describing the discrete outcome of a multifaceted coin, in this case, a dice. Or it can be other discrete events, such as the 4 letters of the DNA molecule, right? Or different choices of the words in the article and so forth. So this distribution is known as the multinomial distribution. And this value of the random variable is often described not by a numerical discrete value like 1, 2, 3, 4, because if you do that, it will make a lot of the calculation a lot more complex. For example, how to compute an average between 1, 2, 3, 4, 1, 5, 6, right? But if you use this representation, which is known as the one-hot representation or indicator variable representation, where you have the number of dimensions equal to the number of possible outcomes, and then on each dimension you have a binary indicator indicating the presence and the absence of that event. Then you put some constraints that only one of these dimensions can take a non-zero value and others has to be all 0. And then that particular event of non-zero for each dimension takes a probability of theta j, where j is dimension. And then you have a now clean way of describing a multinomial distribution, or the distribution for the multinomial random variable. And again, there is a systematic way of writing down the probability, the discrete the probability of this discrete event. For example, here is a almost like a natural language way of describing this, which is the probability of x n of k equals to 1, where k index the dice size and the n indicates the rounds of the row, right? And to make it easier, you can basically, if the k dimension equals to 1, obviously that value equals to theta of k, which is the probability of that case outcome. But if you do not know, what that k is ahead of time, the way to express this very inclusively is to write down this product of theta k raised to the power of x n comma k. Basically, it will help you to select the particular theta that has been picked up by these random events. So it's a cumbersome expression in here, which is a product of k terms. But remember, because we have this one hot property that only one x k is equal to 1, others equal to 0. Therefore, out of these k terms in the product, only one of the theta k will be picked up. Others will be reduced to 1. All right, so this is a typical set of discrete distributions we're going to use in the future very often in machine learning. And once you have this, once you toss the dice or the coin n times, you have a very natural way of estimating the frequency of events, which is pretty much intuitive. It's the count of that particular event over the total number of times of your events. Okay, this is also known as the maximum likelihood estimation, because the way to derive this outcome is to basically write down the maximum likelihood of this event happening n times, and then find a theta that is an argmax of that. And in this case, you are lucky enough to have a closed form event, right? And today, in fact, we're going to talk about algorithms and problems where there isn't a closed form event estimation of those parameters, and how we're going to do it and solve the problem iteratively using some heuristic and algorithms. Now back to the continuous variable. One of the most often used type of continuous random variable are known as the Gaussian variable. And here is a Gaussian distribution for one-dimensional continuous random variable. And we are all familiar with that, right? This is a shape of the density. And there's also a way to write down the shape of the cumulative distribution, probability mass, which is an integration of this up to x. Just a reminder for you how it looks like. And then here, if you have a multidimensional Gaussian distribution, then the probability density of a x vector, given the key parameters in the Gaussian, which is the mean and covariance, you have this quadratic form raised to the exponent. And then also there are some term here to normalize the whole distribution. Okay. And why this is interesting, because today we're going to use these building blocks to build some complex distributions, such as the mixture models we're going to talk about. And having that distribution, again, in the continuous case, also allows you to achieve obtain a maximum likelihood estimation of the parameters. In this case, the mu and the theta, or the sigma. The mu, which is the mean, is again quite intuitive. It is the sample mean of all your examples. Xn is the nth data points. You sum over that and divide it by n. And then the covariance, maximum likelihood estimation, again, is the sample covariance. It is going to be computed from what is known as a scatter matrix that is defined in this way, and then you divide them by n. Very often there are what is known as the matrix expression of the whole data set, where you introduce a matrix X, where each row is that data vector, and you have n rows indicating having n data points. And then this S can be described by a matrix product, X transform text multiplied by X. Okay, and if you have this matrix form, you actually could even compute or determine whether they are full rank, whether this matrix is invertible or not. Why that's important? Because you notice the Gaussian distribution in here. Here, in writing down the Gaussian, your theta or sigma, the covariance matrix has to be inverted. If from the sample estimation in here, you have a uninvertible sigma, that actually becomes a problem, right? We actually will, have a numerical technique to remedy that by putting regularizers, by, adding a diagonal matrix of ones and so forth. But again, these are not the topic of today's discussion. Okay, so then moving on, we have another interesting probabilistic density function known as the conditional Gaussian. And that is for a particular type of data, unlike what we just talked about, which has only, a single type of data that you observe. Here you have two types of data. One is the X, one is the Y. It is pretty much like your classification problem. Y is the label, and the X is the vector observation of, of numbers. And why you have this pair, and why it's called conditional Gaussian? Well, in here, we're describing a phenomenon you can see in this graph, where the X random variables may come from one of the two original Gaussian distributions, and they all have their own mu and sigma. And then which Gaussian component they come from is indicated by the Y. Okay, that's why Y is a discrete random variable using, for example, the multinomial or the Bernoulli I just described. Now you know why I write down the likelihood like this, right? And then X is conditional Gaussian, given that X, Y is known. Once X, Y is known, then you know which Gaussian component it is coming from. For example, in here, we say Y of n comma k equals to 1. That means this nth point comes from the k's cluster or k's Gaussian component. And then in here, you can pick the mu k. And you may wonder where is the sigma? Sigma is in here. It is the same for the two clusters, let's assume. So you pick the k's centroid to write down the conditional Gaussian. But if you don't know the actual value of the Y, or you want them to be very genetic to accommodate any possible assignment of the Y, then you just write down the conditional Gaussian like this: X given Y without making a specific assignment. And then the likelihood becomes now a very interesting expression like this. In the inner bracket, you have a product over k terms, which basically provides you the placeholder of k possible options, okay, of the cluster centroid or of the Gaussian component. And then which one to be chosen is determined by this Y, which is now raised to the power position, because whether they equal to 1 or 0 will determine whether this particular component will be selected or reduced to 1. Okay, and then this outer product of n just tell you we have n data points. Okay, so it's a very neat expression to represent conditional Gaussian. And then for conditional Gaussian, the maximum likelihood estimation is also very intuitive, because you already know that for each point, they come from one of the k possible components. At the end of the day, you are going to estimate the frequency of each component, which is a pi of k. You basically just count this indicator, a variable's configuration, how many number of times this k's component was equal to 1. And then for the mu and also for the sigma, which I didn't write here, you basically just pick those points of X that belongs to k's cluster, and then divided by the total number of times of being in k's cluster, and then you basically can compute the component, the mean of that k's component. Okay, so notice this expression. I want you to be very, very careful in inspecting this expression, because we're going to very soon abuse it or overload it with some other tricks. So here, the way I pick examples is either to use a power kind of a trick to put the indicator into the power position, okay, or I use this multiplication trick where if y equals to 1, they will pick x as it is. If y equals to 0, then x will be 0, this whole thing. Therefore, there is no contribution of that particular point to the estimation of the mu. Okay. My next question will be, what if now I don't have the y, which is actually the case we're going to discuss today in the cluster. Remember, in here, we assume that the conditional Gaussian are modeling data where both the x and the y are given. But in our clustering problem, we only observe the x, not the y. And that's where things become interesting and some heuristics need to be known. For example, in the k-means, this y was actually provided by measuring the distance of a point to the cluster center and then give them a discrete assignment. But there are other ways of doing that. Okay, so now back to our clustering problem. Today, I'm going to introduce a new probabilistic model known as the mixture model to help you write down the likelihood, okay, of this type of data. So what is a mixture model? Well, mixture model, if you want to visualize it, it looks like this. It's basically a combination of multiple components. Each of them may be a Gaussian. Okay, and therefore the density has now, hills and the valleys. It becomes not a nice looking unimodal shape like you see in the Gaussian distribution. But if you want to be a little bit more kind of careful in inspecting this, you may be able to realize that this whole thing may be a addition or summation of 3 component Gaussians, okay, like this. And this z can be taken as an indicator for every point. So every point comes from one of these 3 Gaussian components. Yeah, they come from a single mixture model. But if the mixture model has, say, 3 Gaussian components, then we can safely assume that this particular data point, okay, every data point come from one of the component Gaussian instead of coming from the entire mixture. It is more explicit. And then, a z can be used to indicate that random event of coming from one of the 3 Gaussian components. And this is basically a mixture model. A mixture model is by itself a one model, but it is made up of component models, which can be, inferred by some probabilistic procedures. And why we have latent variables, right? So this z, by the way, here is known as a latent variable, okay, because we don't see it. It's something that we want to introduce as a placeholder for the component assignment of any given data points. And as you can see, the rationale here is to make our inference procedure or mathematical procedure more intuitive and easy. This z may not be something that physically exists. It's a conceptual thing indicating the belonging of a point to a cluster or to a mixture of components, right? But in practice, unobserved random variables or latent variables are actually even more, have more underlying meanings than just a conceptual placeholder for cluster membership. So here I have a few examples. Sometimes it is actually a real world kind of a phenomenon or object, but you don't have, the convenience of directly, observe or measure that. For example, the temperature of a star. It's a real thing that star has a temperature. It's a real physical property or phenomenon, but you cannot fly to the star and put a thermometer there and measure it, right? So you basically observe, the light or some kind of radiation, from that star, from your device, and then you run some procedure to infer, to calculate the temperature of a star. Therefore, the star temperature becomes a latent variable that you need to, infer. The causes of diseases, the ancestors in the evolutionary program have the same thing. We know that we evolved from maybe a certain ancestor, or we were created in a certain way, but we never ourselves see it. You can make them as an unobserved random variable and make inference about that if you accumulate enough current evidence, say, populational data and so forth. Right. And sometimes it is something that you probably, it's still real thing, and also you can measure it, unlike the star or the ancestor. For example, traffic signals and radio signals from your radar and so forth. But you have maybe a faulty sensor, or you have some noise or error in those measurements. Therefore, the thing you measured may not reflect the true value of that physical quantity. You can still basically model this quantity by making them a hidden random variable and introduce a noise model around it, so that you can make a better estimation or provide a confidence interval and so forth. So there are also two types of latent variables. One is discrete, the other is continuous. I talked quite a bit about the continuous ones already, such as temperatures, such as radio signals. But discrete random variables, you already saw it, right? So these are cluster membership of a points, group membership of points. For example, by looking at your behavior in speech or in voting, I can probably make your party affiliation, Democrats or Republicans, as a discrete latent variable. And someone may be interested in making the inference about that to do targeted ads or campaign. Right? And the continuous ones, I already said about that. So latent variables will be a very useful thing down the road that we're going to use a lot. In fact, the entire business of deep learning make heavy use of latent variables in their intermediate layers to do representation learning, feature extractions, and so forth. Now go back to our simple scenario, the Gaussian mixture model or the mixture model. Here we're going to talk about one type of mixture model known as the Gaussian mixture model. Okay, and just to be very, very direct, the expression of the Gaussian mixture model is rather intuitive. You can see, assume that now X follows a Gaussian distribution. Remember, in the past, when we assume that when X follows a Gaussian distribution, then on the right-hand side, you have a exponential expression of the sample deviation against the mean, and then there is a covariance, and then there is a non-linear constant. In here, I make a slightly kind of different statement. I say X comes from a Gaussian mixture model, not from a Gaussian distribution. And then the expression will be now converted into a weighted sum of multiple Gaussian components. So each of these n of X given theta, mu k, and sigma k is what you see before, the Gaussian distribution. But it is actually already assuming that you are picking only the case component of the Gaussian distribution in your, maybe in your catalog or in your library. And then there is a pi k, which is the weight of this particular sample coming from the distribution. Okay, and this is again a very graphically intuitive way of expressing the relationship of those indicator variable and the observed real variable. And then this is roughly a density curve that you can imagine coming from multiple Gaussian distributions. And here is a two-dimensional illustration of that. Okay, so this is a Gaussian mixture model. And I argue that a Gaussian mixture model is perhaps a appropriate model to solve our data clustering problem I just described before. Remember our data points, right, that we saw earlier, which is not as dramatic as this one, but they are kind of like this, a data cloud of multiple clusters. And then in each of them may be modeled by a single unimodal Gaussian distribution. And when you put them together, you actually could model the entire data set. Now let's go a little bit further into the mathematical description or underpinning of a Gaussian mixture model. Okay, so here we know that there are two random variables, x and z. Z is not observed. By the way, in the earlier slides, I may use y. Well, I apologize. They are just the same thing. I just here converting to z because that's actually what's often used in the literature. So we need to write down, a probability distribution of the z because that's actually where everything gets started. You first make an assignment of data points based on some discrete probability, pi of k. And then the likelihood of the sample x can be now written easily using what we just talked about as the conditional Gaussian distribution, because here the k is already given. Okay, so you can basically pick the k's component. And then the likelihood of a sample, which actually does not contain any specific assignment of the z, you don't actually know that, which implies that the x can come from any of the k possible components. Therefore, we're going to put a probability of that assignment here, and then they will be multiplied with the conditional Gaussian likelihood. Okay, so this is the simplest way of using a chain rule to write down the joint probability of p of x and z. X is the observation, and z is the latent component assignment. But note that this particular term, p of z times p of x given z, which leads to p of x and z, isn't the likelihood of our data, because our data does not contain the z. Z is not observed. You only observe x. Therefore, we need to do one step known as the marginalization of the z. Basically, we sum over all possible values of the z so that the z will be eliminated from the joint distribution to make them into a marginal distribution of x. Okay, and so how to make that happen? You plug in this expression, p of z, well, that's already in here, so you plug in this term. Okay, and then you also plug in this part, which is the conditional Gaussian x given z, which is written in here. You just multiply in here. And then we're going to now do the summation over the z. Remember, the z for each data point, okay, in fact, here we're talking about only one data point n. So for that particular data point, z can take, k possible options, right, from 1 to capital K. But remember, it is an indicator function, meaning that at each time, k, only one of the k can be 1, others are 0. Therefore, when you have this multiplication of the k, you are going to, pick up, only, the k's component once. Okay, so for each of these k assignment, when this z equals to, one of the k's, this product will result in one of the terms indexed by k. Okay, and then in the outer summation, you have a k such options, and that basically leads you to this expression, which you saw in the previous slides already. That's why I gave you upfront without a derivation, but in here, you see how they are derived. It is not by a smart guess. It is by a rigorous algebraic derivation from a Gaussian mixture model. So in here, just some jargons, right? So in here, people call this pi of k the mixture proportion or mixture weights, and the n of x given mu k and the sigma k to be the mixture component. It's a Gaussian component in this case. To be more general, you may have a question, do I have to stick to Gaussian mixtures? Well, the truth is that you don't have to. You can have this particular component to be arbitrary distribution. It's just like Gaussian is very easy to write down and easy to compute. So that's becoming a favored form to produce the mixture components. Okay, so now we have a likelihood function of a sample under a mixture model. And typically in machine learning, that's already, maybe a majority of the game. Once you have the expression of the likelihood, what is the learning task? Maybe I want to pause here first to receive any questions you have so far, and also pose at you a question. Having this already, what is the machine learning task that we want to solve? Anyone want to shout out? Or type your chat in your chat?
Do you want to estimate the mean and covariance of each?
You want to estimate the mean? Yeah, exactly. So this mu and sigma. In fact, this mu and sigma is an expression of two sets of mu's and sigma, right? Mu has k possible mu's and the sigma has k possible sigmas. You want to estimate that. And how to estimate? Well, you have this expression of the likelihood already. You just do a argmax, right? And how to do argmax? Anybody has an idea? You have a function already, and you have an argument in the function, and you want to find the argument that maximizes the function. What do you typically do? You take a gradient, right? In the past, we've learned gradient descent algorithm. You started from a random guess, and if you're lucky, you can basically keep updating from the random initialization guess, and you hopefully can converge, to a stable estimation of those, arguments, right? That could be an idea. In fact, sometimes, in a very simple expression of the likelihood, like the Gaussian or the multinomial, we could even get a closed form expression, right? That's also achieved by taking the gradient to 0, and then suddenly you'll see that the right-hand side of that equation can directly give you a one-step estimation of the whole thing. So taking gradient and be able to use that to solve closed form or solve a fixed point can be a very good approach. Right. I have a question here. Estimation proportion, yes, okay, answer me. Now let's see how does this idea work in the mixture model case, taking the gradient. Okay. Remember that I already said, maybe I didn't, but I want to say now, that for a mixture model like this, the story wouldn't be as simple as you imagine, that having a gradient, you either go to a closed form or you have a very simple gradient that you can use to update and all the way to convergence. The truth is that there are some unexpected complexities that will involve. So now let's look at what could be the ideal case. Imagine that now we observe a fully observed data. Let's imagine there are no latent variables. Okay, so that basically make the mixture of Gaussian model not necessarily a mixture model. It's just it's still a mixture model, but it's fully observed. You don't have a classroom problem. In this case, x and z are both given, and then you write down the log likelihood of x and z. Remember that the joint probability of x and z can be expressed by a product of a p of z and a p of x given z. And under logarithm, they factor into two summand, right? Two terms. And also even nicer, in these two kind of terms, in the log likelihood, the two parameters that you want to estimate factored accordingly. Their factorization is exactly aligned with the bigger term that is factorized. Theta z is only in here, and theta x is only in here. Okay. By the way, a quiz here. I use the theta to generically refer to those are hidden random variables or hidden parameters. In the case of a Gaussian mixture model, what is theta z? The parameters for z, what is that?
Isn't that the pi or no?
It's the pi. Thank you. And obviously here you know also as well, right? That the mu's and the sigmas. Good. And the nice thing is that you can now estimate the pi only by counting the z, and estimate the mu and the sigma only by counting the x, right? With their z assignment already known. But in our mixture model, you know, we have to marginalize out the z. Therefore, there is a very annoying summation sign right outside of the joint probability of x and z within the log. Okay, so therefore we are going to now having a expression of the total likelihood, you know, in a form that is a logarithm of a sum of something, and that actually creates some algebraic trouble. Let's look at how the gradient in this case look like. Now you take a gradient of this log likelihood of a mixture model with respect to, say, any of the parameters that you have to compute. And I don't need to walk through all these equations. You can inspect them maybe more carefully afterwards. But at the end of the day, you are going to have something like this. This gradient over a particular parameter, say pi z, will be rather complicated, right? It's expressed as in here, you know, a sum of component-wise gradient. Okay, this is nice. This is component-wise gradient, but this weights of that component, R of k, includes everything, pi of k and the p of x given, you know, the z value and so forth. And you probably can realize that in here, every parameters to be updated are coupled. The x and the pi and the mu and the sigma will be all present, you know, in this whole derivative, regardless of which particular random parameters, probabilistic parameters you are going to be taking derivative over. All the parameters to estimate will be present in this gradient, although they will be present in different forms, right? So that, of course, makes the whole thing very, very complicated. And also, in every step, you need to compute all these big terms, which is also very, very annoying. You need to compute, reevaluate the x and under a particular component and over the entire mixture and so forth. Right? So it is not as straightforward as what we had before, where you can compute a sample mean and the sample variance and also frequency for the pi and the theta and the sigma. Right? And another numerical difficulty, which is very undesirable, is that even when you are willing to do all this and just to compute the gradient brute force, you lose some nice control over certain properties of the parameters to be estimated. For example, if the theta is the pi we want to estimate. So what is pi? Pi are the frequencies of discrete events, right? So they have some property. They have to be non-negative. They have to be between 0 and 1. And then all the pi's should sum together to become 1, right? When you take a gradient, how can you enforce that kind of constraints? Well, it's tricky, right? And then you can have other constraints. For example, this sigma, has to be positive definite. Otherwise, it is not invertible. Therefore, when you are running just a gradient, you lose control of the sigma. They could take any value, maybe asymmetric, and also maybe not positive semi-definite or invertible. And you will arrive at an estimator that is pretty much useless in the end, either by having negative pi or having ill-conditioned sigma and so forth. Right? So that's basically just some problems that I want to bring forward if we are trying to adopt a brute force gradient algorithm for mixture models. So what I'm going to do next is to present you a heuristic and also some theories behind it to bypass all these difficulties so that we make a mixture model learning problem almost as easy as our fully observed, component Gaussian learning problem. Okay, let's see what's going to happen. Okay, what is RK? I think Daniel, you answered it already. Good, thank you. All right, so what is an EM algorithm? I want to start straight with a algorithm, and then let's try to understand it by looking deeper into the math. So this is an algorithm, okay? Maybe I will describe that first. In fact, I'm going to describe that later. Let me show you the equation first. So we've got, a mixture of k Gaussians, right? These are the equation I just produced. Marginal of the indicator, conditional of the observation, and also the full likelihood. And let's compare, the differences between what we are facing here to what we were facing in the conditional Gaussian, estimator, where everything is observed. So in there, when the z random variable is observed, you can leverage on that to select basically samples for you to compute the estimation. For example, you select those z which equals to k to estimate the frequency of pi k, right? And you select those x whose indicator y equals to k, and then you compute the mu accordingly, right? So this is pretty straightforward, and you can also do the same for the covariance matrix. And because this procedure is very similar, in fact, identical to a routine, standard Gaussian parameter estimation, you have all these nice conditions that these, for example, these multinomial parameters are, non-zero and between 0 and 1 and sum to 1, and all these actually have nice properties and conditions. Now, if z is not observed, the key idea behind the EM is to pretend that they are observed. You basically, impute some value for the z so that you go back from here to subsequently solve a fully observed conditional Gaussian estimation problem. Okay, so that's the trick. So what's the natural thing to do to replace z? Well, you can replace them with the probability of a z equals to a particular class given your current observation of x. And how to compute that? Well, by a very trivial formula known as the ratio of probability. You can basically plug x into one of these components and divide it by the sum of weighted components, and then you can get a probability of x being in one of the components, right? So that's kind of intuitive. So let's see how it goes in practice. So here is a EM algorithm, both in equation and also in graphics. So you start from here, which is a uncolored set of points. Of course, we have the same issue in k-means. You need to start with a guess of the k. How many clusters? We are going to guess it to be 2. Okay, and then something that you are probably familiar with will be happening. You start by guessing randomly the centroids and the covariance of the 2 clusters. Okay, say they are in here and here. You guess them to be centered in here and centered in here, and then you guess the covariance to be standard kind of covariance, basically a diagonal matrix of 1, for example. You can start from there. And then what you are going to do is to do the following estimation of the z. So for each of these points, you are going to compute this quantity, which is the posterior probability of the z label or z indicator given the observation x, or given the position of x, and also given your current value of the parameters, the mu and the sigma at time iteration. This little script t indicates the time iteration, okay, the tth iteration. Now you are at iteration 1, so t equals to 1, okay. So you can imagine that each of the points will have a fractional probability of being in one or the other Gaussian component, depending on how closely they are. Right? So k is you can call it a hyperparameter or call it a unknown constant. Okay, just like in k-means, you just set the k to be 2 or 3, whatever. Okay, and we said already that there is a issue about estimating the k, but that's a advanced topic, maybe in later machine learning, known as a non-parametric base. But here we assume k is already a given quantity for the sake of making things a little bit easier. Okay. Okay, so yeah, EM algorithms always assume that you are given a fixed k already. So now let's go back to our first iteration. Once you estimate this, you can imagine that this is equivalent to assign a color or maybe a fractional number of each point. They can be very red if they are very close to the red centroid. They can be very blue if they are very close to the blue centroids. But they can also be somewhere reddish and bluish if they are somewhere in the middle. So you can imagine how this particular point may have a p of z given x to be half-half. That's possible. Or maybe 0.4 versus 0.6. Right. Okay, so now you are going to keep all this estimation. That's why it's called the E step. It is the estimation of the probability of a data point x being assigned to one of the k possible clusters. And then you're going to the M step. In the M step, you are going to compute now the phi, the pi, the mu, and the sigma by assuming that the z are no longer a hidden random variable. They become observed. Their value are replaced by this guy, which is a fractional number. Okay, it's not a 0 and 1. It's a fraction between 0 and 1. And you are going to now do a summation over that. Look, in here, the summation is over n, okay, which is not basically only the number of points belonging to one of the components, because every component can belong to the component just with a different fraction of weights. Therefore, you are going to sum over all the points. And then you divide them by n. And that gives you the first iteration estimation of the frequency of the components. And likewise, you do the mu. Remember, in the past, I have x times a quantity called y, which is the label of the data points, right? And y is discrete, either 0 or 1. In here, I multiply x by tau. Tau is a fractional number. I'm literally saying that this particular point, x, can be kind of cut into half, and or a particular type of a breakdown, that a portion of that goes to the red cluster and a portion of the other goes to the blue cluster. And then you compute the mu accordingly based on this fractional contribution of every point. And likewise, you do the sigma. You can see that everything else, this part, is the same as our conditional Gaussian estimation, except that now this weights, okay, is computed in the E step to be the probability of the label, okay, given the data points. And then what's happening is that after you estimate this, and then you want to continue and now re-estimate the weights, because after this round, you can see that this particular two centroids and covariance won't be as naive as this one. They probably will be moving closer to the data cloud. And also their shape could reflect more on the distribution of the data clouds. And therefore, you are going to redo the assignment of every data points. And you can see that some of the points, like in here, gets reassigned to be more blue, and here they are going to be more red, and then you recompute, and you to go on and on until convergence. Okay. So that's the EM step. In the initialization, they are also, in the initialization, someone asked, how do I initialize this? They are random variable. Yeah, you initialize them to be 1, to be 0.5, for example. That's a safe way to initialize. Okay. Does this sound familiar to the k-means algorithm that you heard earlier? Right, so it's almost kind of in spirit the same. You basically get some assignments of the data points, to some particular cluster components, and then you recompute the cluster center and the cluster weights. But in here, you also compute the cluster covariance matrix because it is a mixture model of Gaussians. Right. Is that the result deterministic? We'll see whether it is deterministic or not. Okay, we'll see very soon. So let's first record the k-means, right? If you look at these two equations in here and in here, the differences are actually quite explicit, but not very, very strong, right? Here, the z is a discrete assignment that you do an argmax of this, right? You basically, in fact, I think it's argmin. Sorry about that. Okay, it's going to be picking the closest kind of a points center that I'm going to belong to. And then in here, you are going to now count every data point in a hard fashion. It's a hard assignment. It's a delta function that you either are in this cluster or in the other cluster. But in here, you have what is known as the soft assignment. Right? Therefore, EM algorithm is often also known as the soft k-means, or the k-means is also sometimes known as the hard EM algorithm. Okay, but the procedure are the same. You can see this E and E-ish and M-ish step in the k-means algorithm. Okay. Now, I think we're ready to answer a few additional technical questions. Is this whole thing going to converge or deterministic? Well, certainly not. Depending on your initialization and how you pick the initial assignments, it is very possible that you will be getting to different convergence. Because this entire likelihood function, let's go back to this. The mixture model likelihood function like this, it is not a convex one, right? It is actually a multimodal one. Therefore, the likelihood loss function surface has valleys and hill. If you pick from here, for example, you maybe go down to here, but if you pick from here, they will go outside. Right? So that's actually the same thing you experience already in the k-means. Therefore, practically, people will do multiple random restarts, and after converge, they will compute the likelihood of all data with the final estimation and compare a few alternatives and pick the best one. Okay, now let's see. What's basically why this algorithm makes sense? What's the what is actually happening? During the EM algorithm, because originally we say once you have a probabilistic function, you are going to do maximum likelihood estimation. For this EM algorithm, I don't know yet. I'm just telling you a procedure. I didn't tell you what particular loss function has been optimized yet, right? So we need to actually talk about that. All right, no more question. First of all, yeah, again, another iteration of this identifiability issue in the mixture model. It's not necessarily very identifiable because of the terrible, irregularity of the likelihood surface. Right, so we answered that. The other is how that algorithm, this algorithm seems to be very neat. How is this derived? Okay, and hopefully you can derive it at some point. So here I will give you a complete derivation of the EM algorithm so that it is not, in the end, a heuristic. It is really a principled procedure of a optimization problem. Okay, so we start from here. We've seen Gaussian mixture models already 3 times. Okay, and at the end of the day, we conclude that the likelihood of a sample in here is not a good target to optimize, right? Because the gradients is complex and so on and so forth. Now put the EM algorithm aside. Let's say having this, how numerically we can maybe navigate through to still allow us to maximize this particular term without directly solving this problem. So here, let me introduce another concept known as the complete likelihood. Okay, complete likelihood is basically in here, the likelihood of all random variables that matters, regardless whether they are observed or not observed. So in this case, for example, Z is not observed, but we put it anyway. So it is the joint of X and Z. We call them complete likelihood. Now, in the case of a mixture model, you probably already realize that this very definition of the complete likelihood itself is a random variable, right? This one is an unknown fixed quantity. We know it's a fixed quantity, but it's unknown. But in here, we know that it is a random variable. Because why? Because Z is a random variable. It is already written into, the complete likelihood definition. Therefore, this is a variable that is you cannot take a derivative over a random quantity, right? Okay, so now let's see how can we proceed. Well, complete likelihood has a nice property, which is that it factorize, right? If you take a logarithm, they factorize exactly along the Z and the X, so that pi and the mu are decoupled. Now let's see what will happen if Z is not a constant, but a variable of that is unobserved. Well, what you can do is you can turn this whole thing into a deterministic quantity by remove the randomness, right? One way of removing the randomness is to take expectation of this random variable, this complete likelihood, with some distribution over what is random, say the Z. So here I'm going to take a expectation of this random log complete likelihood over a distribution of Z given X. Okay, I choose the distribution to be P of Z given X, which is the posterior of the hidden unknown label given the observation. So this is always well-defined, and we know that we have a way to compute it. Right? So if this is known, then this expected complete likelihood also factorizes. Okay, it factorizes the way very similar to the original complete likelihood, except that now the Z are replaced by an angular bracket of the Z, which is the expectation of Z under some distribution. Okay. Okay, now let's see what's happening. Let's imagine that suppose this, I have a question here. Why is P on the lower right? Oh, okay, this is just a physicist expression. When you take expectation over a random quantity over certain distributions, it is a shorthand to put that distribution here to remind that over which distribution the expectation was taken from. Okay. So now let's imagine that this guy becomes our target of objective. And let's see what happens when we maximize this expected likelihood iteratively. Okay, we use the following procedure. In the E step, remember that the expectation was taken on in the P of Z given X, which actually is unknown yet. Therefore, in the E step, we're going to compute exactly that, P of Z given X, given our current estimation of the mu and the sigma. Okay, so this is the expression. Okay, this is the fraction of a mixture component probability versus the entire mixture probability, and that gives you the probability of this particular data point xn being in a particular component. Okay, and this particular step where we compute the posterior probability of a hidden random variable given the data is also known as inference. In larger models, as we are going to see in the future, such as in the hidden Markov model, we may be computing any hidden random variable given any observations using a procedure far more complicated than this one. Okay. And then let's see what's in the M step. Now assume that we have what is supposed to be in this lower index of the bracket already estimated, which is the P of Z given X, right? And then we're going to be able to now, treat them as observed, right? And remember, in our conditional Gaussian distribution, we know how to estimate the maximum likelihood estimation of a fully observed, a mixture model where Z and X are both given. I showed the equation earlier already, right? So in here, you just plug in because your P of Z given X is already given as the bracket, angular bracket of Z. So I'm going, or the tau, right? Sometimes I call it the tau in here. So I'm going to plug in, this exactly, and then do a maximum likelihood estimation of that, right? So as you can see, the EM algorithm is literally about realizing our estimation by maximizing the complete likelihood. First, computing the expectation of the expected log likelihood, and then maximizing this by plug in, those Z estimations. Okay, that's basically how the EM algorithm was derived. It is derived from writing down the complete likelihood of data. And in here, all these situations can be easily satisfied because it is a closed form expression, of the sample, into the covariance and also the mu. Okay. So as I just mentioned, this is isomorphic to the MLE, except now that the random variables that were originally hidden are now replaced by their expectations. Okay. Does the EM algorithm work for arbitrary parametric data? Can you elaborate a little bit more by what do you mean by arbitrary?
Yeah, I was just wondering, like, let's say I had a certain method of generating data, like just say from any arbitrary distributions, like mixture of Gaussians, like then would it be like what are the conditions basically for EM to accurately?
Very good question. Yeah, in fact, EM is a procedure, right? Its success actually highly depends on the assumption of the model. In here, for example, what is actually more important than EM is the Gaussian mixture model, because that's basically allowing you to write down all this formula in a very explicit parametric form, right? But if you generate the data from some very complex distribution, for example, the nowadays very popular GAN model, the generative adversarial network models, which is obviously way more complicated than the Gaussian mixture model, then your EM algorithm need to count heavily on your design of those component models. And to the point that nowadays people use a full inference network, or a decoder, for example, to represent that generative or the inference process. But these are topics which will probably not cover in 701. But if you are interested later in 708 graphic models, there will be extensive discussions of that. But yeah, EM algorithm itself is a sound algorithm that is used in all these procedures.
Thank you.
All right. I'm going to skip this. You've seen k-means now 4 times, so you probably already know how they connect to the EM algorithm. I will talk about the theory now. Okay, so for example, you may already wonder, okay, you basically are maybe solve a confusion by introducing yet another confusion. We know the EM algorithm is a procedure that comes out of some smart design. And now we know that it is designed from a complete likelihood, but complete likelihood is not likelihood. Still, it can be puzzling what is going on. Why, for example, maximizing the complete likelihood is a legitimate thing? Why not something else? Maybe why not say, entropy or whatever other terms, right? So the theory hopefully gives you another layer of clarity. I claim that what's happening underlying the EM is just a very clever way of solving the vanilla, the original maximum likelihood estimation problem for the mixture model. This expected complete likelihood is just a vehicle to attain you a nice approximation to that quantity that we're going to optimize. Okay, right. Okay, so we say that this is difficult, then what we do? And we also know that there is a complete likelihood and an incomplete likelihood, which is our true target to optimize. Right? So what's the relationship between this guy and that guy, and also the expectation of that guy? Right? So here is a relationship. Basically, we know that Z is not observed; it's hidden variable. And to turn the hidden random variable into something that is more manageable, one needs to introduce any arbitrary distribution, Q of Z. Remember, in the past, just now, I introduced the P of Z given X to be that distribution, but you don't have to choose that. You can choose arbitrary anyone, as long as they give a probabilistic distribution of the Z. It could be a uniform, for example, although it is not very good. And we can say why it is not very good in a second. Right? But given that, you are not able to define a expectation over the complete likelihood. And here, I want to introduce an important concept so that you can establish this term versus the incomplete likelihood I just introduced. So this term is this concept is known as the Jensen's inequality. Okay, which basically says that if you want to, establish a relationship of the log of the sum of something versus the sum of the log of something, there is a explicit inequality relationship between these two. Okay, the log of the sum, weighted sum of say anything. In here, this term, but it could be other terms, okay, is going to be strictly greater or equal to the weighted sum of log of that function. Okay, so this is known as the Jensen's inequality. And geometrically, it is very intuitive to understand it because this part, the log of something, is actually this log curve. Right? The sum of logs is about picking 2 points or any points, inside on the log curve, and then draw a line between them and find somewhere in the middle. Because this weighted sum, by the way, this is I should be more strict. It is not only a weighted sum; it is a convexly weighted sum. Okay, convex is another complex word. It means that the weights in here are the weights that sum to 1, and each weight is between 0 and 1. So this is known as the convex combination of a term, of a function, right? So that convex combination, is always lying between basically the extreme point, okay, of the convex set. In this case, the line of this connected by this connecting to these 2 points, 2 extreme points. So this line is always below this log curve, right? Because log is a convex function, therefore it is always above that. So this is a proof by visualization. And we use this proof to actually now establish something that is very important. Because on the right-hand side, or on the left-hand side, what's that? This is the logarithm of our incomplete likelihood, which is our true objective, right? The likelihood of the data of only X. On this part, on the right-hand side, you actually have 2 terms. Log of P of the complete likelihood divided by the Q of Z given X, okay? And unfortunately, I don't have a pen here, but you can see this part is what? Someone want to give it a try?
It's the expected value of the complete likelihood.
Yes, yeah. exactly, thank you. So it is a sum of a Q of Z times the log of a P of the complete likelihood, right? And then there is another term, which is the sum of a QZ log of QZ, which is what? The entropy of the Q distribution, right? Okay, so, and then there is, this one is strictly a lower bound of that. Therefore, our expected complete likelihood is now a lower bound of our true likelihood. Remember that in the EM algorithm, we were trying to push this term. And this term is actually a bound of our original target objective. You can see that there is a rationale already. Maybe you can imagine by pushing this particular term very high, you also at the same time are pushing this original loss function to be very high. Right? So there is this synergy between these two terms. Now let's get a little bit more rigorous. Okay, what's happening is the following. Let's introduce a term known as the free energy, okay, which is exactly that lower bound that I'm going to recopy, okay? And I claim that in the EM algorithm, what is happening is that in the each step, you are actually doing something that is trying to find in the space of all possible Q distribution. Q, remember, is the distribution of the hidden random variable Z. You're going to find the best such distribution that maximize this lower bound, the free energy function. And then, and you hold, of course, the other dimension, theta, which is the parameters of the distribution to be fixed. You hold that constant. And then in the M step, what is happening is that now you hold the Q that you just achieved constant, and then you maximize, the theta, maximize the F with respect to theta only. So this approach is sometimes known as a coordinate ascent approach. Imagine that you plot the loss function F like this, and your optimization space is Q and theta. Then what's happening in the EM algorithm is that you are going this, that in a zigzag fashion to achieve optimality. Okay, so it's a coordinate ascent algorithm over the loss function. Okay. Question? Okay, why they are asking in the E step why that is maximizing? Good question. I'm going to answer that exactly in the next step. All right, so now in the E step, let's see why taking that particular choice makes you the best choice. So let's look at the F, what it looks like. Well, it looks like actually the F is a general term, which could depend on the choice of the Q, right? Now let's say we set the Q to be P of Z given X, right? Remember, it basically out of all possible distributions of the hidden variable Z, we choose that distribution to be P of Z given X, the posterior of the hidden variable given the observation under current estimation of the model. Now let's plug in. We just plug in this into F. And something very magic happened. Okay, this will cancel. And at the end of the day, you actually will have a log of the P of X itself. Okay, so this is a little bit tricky, but what I'm trying to say is that by picking the Q of Z in a particular form, which takes the form of P of Z given X, suddenly your so-called lower bound, F of the original loss function, close the gap between the bounds, okay, and become equal to, the upper limit of that bound. And that's why we say that this is the optimum choice you can ever have. Did I explain to you that? Any questions? Okay, so hopefully now you get at least one point that in the E step, you actually, by making the right choice of the Q to be P of Z given X, you already achieve a step that optimize the F in the p direction. Well, it is optimized because it's reaching already the upper bound, nowhere else to go. That's why it is optimized, right? And then in the E step, in the E step, after you get this estimated, what's the practical consequence? Well, the practical consequence is that now your Q is replaced by, this P of Z. It's becoming a plug-in, and therefore your objective, the complete log likelihood, is now, put under expectation of this P of Z given X, which is exactly what we showed earlier in the E step, right? And then in the M step, you are going to now optimize this particular term, right? And that's what we see earlier as well, which we compute, all the theta, the pi, the mu, and the sigma, that optimizes this particular term by holding the Q constant, of course, fixed at this point. Therefore, they will only play a role in computing the expectation of the complete likelihood. Okay, I will take a pause here. Any questions at this point? Okay, I'm just about kind of finishing the main stuff of this lecture. So here's a summary, right? We've gone into 3 steps, in understanding what is EM. First, it's just a heuristic kind of a procedure that we replace the hard assignment, of data membership of components by a soft assignment. And we claim that the soft assignment is achieved by computing the probability of a Z given X, right? And then we say that we have that particular formula of the E and M because we are computing the complete log likelihood and also the expected complete log likelihood and also maximize that. That's how we get to the formula of the EM. And then finally, our third layer of EM study, we dive into the theory and we say that maximizing the expected complete likelihood makes sense because it is defining a lower bound of the true likelihood of the data. And our EM algorithm is a coordinate ascent procedure that maximizes this lower bound in the direction of Q and in the direction of theta alternatively. Okay, so that completes the EM algorithm at its core. There are some variants which I'm not going to talk too much about. You can go through the procedures by yourself, which sometimes results in more complicated algorithms, such as in the M step, you can continue to run an inner loop that goes gradient and so on. And in the sparse algorithm, you may try to subsample data and not using all the data to update the next round of estimation and so forth. But these are just heuristics people practice. And also there's another heuristic, which is to pick the number of K. I said it already, you pick different Ks. And at the end of the day, you compute the likelihood of data under different estimations, and you pick the best one. All right, so I'm going to stop here. This is your take-home message, a reporting card for the EM algorithm. And in the supplementary, I have some fun deck telling you how to use the same algorithm to estimate fancier models, like a hidden Markov model. That algorithm was not known as EM. It's known as a forward and backward and bound wash. You have all these fancy names. But at the core, it is statistically a EM procedure. That's why I say at the earlier QA, EM is a very generic procedure. In fact, the current neural network forward pass and backward pass of neural network training can be also understood as a variant of the EM algorithm. You are basically performing E and M, in an alternating fashion. Okay, with that, I'm going to close here. Any last-minute questions you may have? Super, looks like you are all happy. We'll see you next week then. Bye-bye.